First, I'll say what I think the standard view is, so I can contrast my view with the standard view, which most of my colleagues in cognitive neuroscience just take it for granted that, of course, neurons exist when they're not perceived, and that neural activity and brains more generally are responsible for conscious experiences in humans and perhaps other animals as well. And maybe if you have the right programming and circuits and software of some AI, it'll eventually be conscious as well. So this approach to consciousness that says neurons exist when they're not perceived, and neural activity is responsible for the generation of consciousness, I think runs afoul of modern science, modern physics in particular. That the Nobel Prize in 2022, last year, was awarded to 3 physicists for confirming experimentally what quantum theory seems to predict theoretically, that local realism is false. The local realism is the claim that, realism is the claim that objects have definite values or properties like position and momentum and spin when they're not observed. So the electron has a position even if no one looks. And locality is just the particles obey Einstein's space-time laws. Things can't travel faster than the speed of light. Influences. So local realism is false. And I think that we should recognize that local realism is false. Neurons simply don't exist. They don't. Well, put it this way: they don't have any position when they're not observed. And if something doesn't have a position, it's not there, right? If you don't have a position, you're not there. So I would say that neurons simply, that right now, I don't have any neurons. And someone who's hearing my argument might say, yes, I completely agree with you now, that you don't have any neurons. But I'm saying I don't have any neurons. If you opened up someone's skull, you would find neurons, but you would be creating them on the fly when you observed. And that's, again, in line with what quantum theory says, is that these particle properties emerge in the act of observation, and they're a result of the observation, but they do not exist prior to the observation. And there are, by the way, in quantum theory, cases where you can set up empirical, experimental situations where you can prove that if you make a certain measurement, you'll get a certain outcome with probability 1. And you can also prove that outcome could not possibly be there until you made the observation. So I'll say that again. You can prove in these special, and if you want to see the paper on this, it's Chris Fuchs. It's 2010 paper on quantum Bayesianism. He goes into this. So you don't have to rely on me. You can read that paper and read for yourself. A quantum experiment that gives you a case where you can prove that you will, if you make this particular measurement, get a certain value with probability 1. Probability 1. But you can also prove, given the detailed setup of the situation, that it's impossible, logically impossible, that the value of that outcome existed prior to the measurement. So this is what you can set up in quantum theory, and that's why a lot of people realize that local realism is false. And it took the Nobel Committee decades before they gave the Nobel Prize for it, because this is a big one, right? So they had Clauser did a lot of work decades ago, and then they were tightening, closing the loopholes and so forth. And finally, the Nobel Committee said, "Okay, what can we do? This is pretty." So I think that it's just in keeping with what physics is telling us to let go of local realism for neurons. And so I would say no, neurons do not exist when they're not perceived.
Philip.
Yeah, so I think Don and I have more in common than that divides us. Crucially, our fundamental starting point is that consciousness exists at the fundamental level of reality. Well, I don't know if it's a starting point, but it's a crucial aspect of our view. I suppose where this first question gets to the heart of maybe where we disagree, namely on the status of physical reality. So I think Don, he can speak for himself, but defends a view that philosophers have traditionally called idealism, which usually comes with the idea that the physical world is illusory in some sense or not fully real. Whereas I guess I'm more inclined to the view that the physical world is entirely real and independent of our minds. This Batman cup is really out there in the world, and lights bouncing off it, and it's made up of particles or fields or whatever. It's just that those particles and fields are ultimately made up of consciousness in ways we could perhaps get into. But and I suppose that the reason I'm there is, I'm totally open to Don's position. So I suppose my view is sort of, in a way, I always go for the middle ways, a middle way between the physicalist or materialist position and the idealist position. I'm open to Don's position, but I suppose I'm just not totally as yet persuaded by his arguments, as intriguing as they are. Don often appeals to these speculative theories popular, not fringe at all, popular theories in theoretical physics, according to which space and time don't exist at the fundamental level of reality. They're rather emergent. But I organized a conference on panpsychism in the States, and Don kindly gave a talk, and Sean Carroll was the in-house skeptic of all this business, and Sean's response to Don that I kind of agree with is, just because space and time don't exist at the fundamental level of reality doesn't mean they're not real, right? It's we discovered atoms are not fundamental; they're made up of quarks and electrons. That doesn't mean we say, oh, there's no atoms. We just say that they're not fundamental. So I'm not on the local realism. I mean, this is going to quickly get outside of my skill set, but my understanding, talking to people like Tim Maudlin, is that none of this rules out for the Bohmian view, for example. Although I know that's not an incredibly popular view, but even if you go for a more popular interpretation of quantum mechanics, we don't have to crudely think particles are the fundamental things. It could be, the wave function is the fundamental physical reality. Sean Carroll tells me he believes in the fundamental reality as a vector in high-dimensional Hilbert space. So we could have some esoteric fundamental physical reality, but which three-dimensional space and time emerges from? This is a heated debate in philosophy of physics. The popular view, I think, is that people like David Albert, Alyssa Ney, try to make sense of three-dimensional spatiotemporal mind-independent reality being real and genuinely emerging from the more non-space-time, esoteric, maybe quantum wave function reality that physicists currently are inclined to think is at the fundamental level of reality. So maybe the normal world we perceive is real but emergent.
Don, it would be useful at this point to characterize the definition of real.
Great points, Philip. Of course, great points. So, the word real, right? We use the word real in a couple different senses, and so maybe we want to distinguish a couple of senses of real. So, one version of real is something is real if it exists even when it's not perceived, and I think that's what perhaps you were saying. But there's another sense in which something is real. For example, if I have a headache and I complain about this nasty headache that I've got, that headache wouldn't exist if I didn't perceive it, right? So my headache isn't real in the sense that I just gave before, that it would exist even if it weren't perceived. And nevertheless, someone might say, well, if you don't say my headache is real, I beg to differ you. My headache is real. So there's a sense in which something is real if it's a real subjective experience, and we, in that case, we know that we're saying something's real not because it exists even when it's not perceived, but rather it exists in my perception. And the question about are neurons real is, I'm really asking, are they real in the sense that they would exist even if they're not perceived? And I think your answer is yes, they are real in the sense that they would exist even if they're not perceived. And I'm saying no, that they're only real in the sense that they are subjective experiences that we have, and so they exist while we have the experience, and they don't exist otherwise. Okay, so just that notion of real, because people can wobble on that and get confused on what we're discussing.
Often I feel like my brain is getting in its own way. I know what I should do. I know what's good for me. I just can't seem to bring myself to do it. I'm sure many of you can relate to racing thoughts keeping you up at night, or just that general feeling of being held back, even undermined by your own mind. That's where therapy comes in, and BetterHelp is here to make it easier than ever. I've personally enjoyed how specific they pair you up with a therapist. They ask you a slew of questions about what type of therapist you want, what their gender is, their religious beliefs. For instance, maybe you want something more secular or more tactical. Maybe you want spiritual wisdom from a specific religious text, or maybe you want to integrate more meditative practices if you're more Easternly inclined. It's astounding how much effort they put into ensuring that you're well matched. BetterHelp is entirely online. It's designed to be convenient, flexible, and suited to your schedule. Just fill out a brief questionnaire. For myself, it took approximately 12 minutes. And then within 2 days, you get matched with a licensed therapist. You can also switch therapists at any time for no additional charge. So, make your brain your friend with BetterHelp. Visit betterhelp.com/toe today to get 10% off your first month. That's BetterHelp, HELP.com/TOE.
So then my take on it is, of course, physicists are going to debate, and Sean Carroll doesn't think that we need to worry about space-time is doomed. But so we'll have to see where the physics goes in this. But here's what I see happening in the last 10 years. For the high-energy theoretical physicists who are working on this, they're finding that space-time. So what they argue is that space-time is doomed because it has no operational meaning at 10 to the minus 33 centimeters, the Planck scale. And it's not that there are pixels at 10 to the minus 33 centimeters. It's that space-time makes no sense anymore. There's nothing you can do operationally with it. And from my point of view, it's a fairly shallow data structure. It falls apart at 10 to the minus 33 centimeters, not 10 to the minus 33 trillion centimeters, just 10 to the minus 33. And it's useless after that. And 10 to the minus 43 seconds. Not 10 to the minus 43 trillion seconds, 10 to the minus 43. So it's a fairly shallow data structure. And so in the last 10 years, physicists have been saying, well, what happens if we let go of space-time completely? And also quantum theory completely, and look for some deeper structures beyond space-time and quantum theory. Can we find anything that can actually do work, like predict scattering amplitudes of particle collisions in the Large Hadron Collider and so forth? And in the last 10 years, so this is all relatively new, they've discovered that, yes, you can, that you can actually, there are these new structures like the decorated permutations and amplituhedra that lets you compute actual scattering processes in space-time. And they have two advantages. What they've discovered are two advantages over space-time physics. One is that, first, if you do it inside space-time using quantum field theory, just to compute one interaction, like two gluons hitting each other and four gluons spraying out, is hundreds of pages of algebra and millions of terms. It's a mess because you're doing it all on quantum fields and space-time. You're enforcing quantum theory and relativity theory. When you let go of space-time and these new structures, you can do what was millions of terms in 3 or 4 or 5 terms. You can compute it by hand. So the math all of a sudden becomes simple. Well, simpler. Physics is never easy, but simpler. And the second thing is you see new symmetries. There's something that they call the infinite Yangian symmetry, which you cannot see in space-time. But when you let go of space-time, all of a sudden you see not only does the math become simpler, but you're seeing new symmetries that are true of the data that can't be seen inside space-time. So what seems to be emerging is that space-time, which we've taken to be the fundamental reality, looks more and more like a, frankly, pretty shallow, tired data structure that is a really bad framework. We're sort of stuck with this data structure in terms of our perceptual, way we perceive the world. And so what physics is doing is now realizing we don't have to be stuck with either quantum theory or special or general relativity. We can go beyond them. And we can then project back into those space-time data structures and get answers much more easily and see deeper symmetries. So it's in that sense that I'm thinking space-time is like flat Earth. It's good for some things, but if you're trying to build a space program, flat Earth isn't going to do it. And if you really want to understand the nature, and space-time is great for certain things, but if you really want to understand the nature, I think, of consciousness and of reality more deeply, a data structure that falls apart at 10 to the minus 33 centimeters is not a good candidate for, and I certainly wouldn't want to be stuck with that really shallow data structure in my thinking in terms of these deeper questions. So,
Okay, Philip.
Well, I suppose, again, I think all of what you've said builds a case, and I couldn't get into the physics of debating that case, but a case that space-time is not fundamental. The fact that our models seem to collapse below certain levels suggests they're of limited applicability, and hence that they don't exist in the fundamental story of reality. I mean, you said Sean Carroll's not sympathetic to space-time being doomed. Well, I think he is. If by space-time being doomed, that's just a sort of poetic way of saying it doesn't exist in our fundamental story of reality. And but yeah, I still think. Suppose we think, space-time is emergent, and what we have at the fundamental level is the wave function. I mean, there's going to be, I presume, a sort of mathematical mapping from the wave function to any state of affairs in ordinary, quote unquote, three-dimensional reality. And so on that basis, we can perhaps make sense of some kind of emergence relationship, or philosophers tend to call this grounding. Scientists tend to talk of emergence. But yeah, I guess I don't see why this means neurons can't exist unperceived. Why can't we just say they exist unperceived, but their existence, when unperceived, is ultimately rooted in a more fundamental story that is not spatiotemporal, for all the reasons you've raised. But yeah, I suppose that's what I think.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.